June 15, 1944. Approximately 8,000 feet above the Imperial Iron and Steel Works at Yawata, Kyushu. Warrant Officer Sadamitsu Kimura of the Fourth Air Regiment pushed his Kawasaki Ki-45 Toryu into a diving attack from the darkness, his eyes fixed on the massive silver bomber illuminated briefly by searchlights below. The B-29 flew steadily through the night sky, its 4 engines producing a deep rumble that seemed to shake the very air. Kimura had been briefed on these new American superbombers. He knew their size, their range, their payload capacity. But nothing in the intelligence briefings had prepared him for what he was about to experience. He positioned his fighter for a standard stern attack, the same approach that had worked against Chinese bombers, against older American B-17s encountered earlier in the war, against every bomber he had ever intercepted. His finger tightened on the firing button. The distance closed. And then, without warning, trace of fire erupted from positions he had not expected. Not just from the tail, where every bomber mounted guns, but from above the fuselage, from below the aircraft, from blisters along the sides. The streams of .50 caliber fire converged on his approach vector with mechanical precision that seemed impossible for human gunners to achieve. Kimura broke off his attack, his heart pounding. The tracer rounds had passed within meters of his canopy. He pulled his fighter into the darkness, confused and shaken. How had the gunners reacted so quickly? How had multiple gun positions engaged him simultaneously from angles where he should have been invisible to individual turret gunners? What Kimura did not know, what no Japanese pilot attacking that night understood, was that he had just encountered a weapons system unlike anything deployed on any previous bomber in aviation history. The B-29 Superfortress carried a General Electric central fire control system that allowed a single gunner to operate multiple turrets simultaneously through an interconnected network of analog computers, servo motors, and electrical fire control that transformed the bomber's defensive armament from a collection of individual gun positions into a single, coordinated defensive weapon. The remote-controlled turrets covering every attack angle represented more than advanced engineering. They represented a fundamental reimagining of bomber defense that American designers had developed specifically to counter the exact tactics Japanese fighter pilots had perfected through years of combat experience. And for the pilots of the Imperial Japanese Army and Navy Air Forces, this technology would prove as deadly as it was incomprehensible, shattering assumptions about bomber vulnerability that had guided Japanese fighter tactics throughout the Pacific War. The story of how American engineers revolutionized bomber defense, and how Japanese pilots gradually discovered the terrible truth about the B-29's capabilities, reveals the widening technological gap that characterized the final years of the Pacific conflict. The weapons system that shocked Warrant Officer Kimura that night would fundamentally alter the calculus of air combat over Japan, forcing Japanese fighter pilots to develop increasingly desperate tactics to counter bombers whose defensive firepower exceeded anything their doctrine had anticipated. The journey to that moment began 3 years earlier, in a conference room at Wright Field, Ohio. January 19, 41. More than 3 years before the first B-29 would fly over Japan, American aeronautical engineers confronted a problem that had plagued heavy bomber design since the concept emerged. How do you defend a large aircraft from fighter attack when that aircraft must carry tons of bombs across thousands of miles? The traditional solution involved mounting gunners in turrets throughout the aircraft, each man responsible for a sector of defensive coverage. The B-17 Flying Fortress and B-24 Liberator both employed this approach, with gunners stationed in nose positions, dorsal turrets, ball turrets, waist positions, and tail turrets. The system worked, after a fashion, but carried significant penalties. Each manned turret required space for the gunner, adding weight and complexity to the aircraft design. Gunners in open positions or unpressurized turrets endured temperatures far below zero at high altitude, wore bulky heated suits, and fatigued quickly during long missions. The ball turret, suspended beneath the fuselage, trapped its gunner in a space so cramped he could not wear a parachute and could barely move for hours at a time. The waist gunners stood at open windows where hurricane-force winds at altitude made accurate shooting difficult and hypothermia a constant threat. And critically, each gunner could only operate the weapons in his immediate position. An attack from directly ahead might engage only the nose gunner, while the dorsal and ball turret gunners, who could not traverse their weapons to cover that approach, simply watched and waited. The inefficiency was obvious to American designers studying the problem. What if gunners could be stationed inside a pressurized, heated compartment where they could work effectively for hours without fatigue? What if a single gunner could control multiple turrets, concentrating defensive fire against a single target from several positions simultaneously? What if the entire defensive armament could be coordinated through a central fire control system that computed lead angles, compensated for aircraft motion, and corrected for ballistics automatically? The technology required to achieve this vision existed, but had never been integrated into an aircraft system. Analog computers had been used in naval fire control since the First World War. Remote-controlled turrets had been tested in experimental installations. Servo mechanisms could translate electrical signals into mechanical motion with precision. The challenge was combining these technologies into a system reliable enough for combat operations and compact enough to fit inside an aircraft. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. General Electric's armament department accepted the challenge in 1941. Engineers assembled a team specifically to develop what would become the Central Station Fire Control System. The specifications were daunting. The system needed to control 4 remote turrets plus a manned tail position, provide sighting stations for multiple gunners throughout the aircraft, compute firing solutions automatically for targets moving at high speed and various ranges, maintain synchronization across all connected systems through electrical networks spanning the length of the bomber, operate reliably at altitudes exceeding 30,000 feet where temperatures dropped to 40 below zero, and withstand the vibration, G forces, and electromagnetic interference inherent in combat operations. The engineering team, led by specialists who had developed naval fire control systems and industrial automation, attacked the problem systematically. They began with the fundamental question of turret design. Traditional manned turrets required enough space for a gunner, his ammunition, oxygen supply, electrical heating, and the mechanisms needed to traverse and elevate the weapons. They were large, heavy, and created substantial aerodynamic drag. A remote turret, with no human occupant, could be dramatically smaller. The gunner's station could be elsewhere in the aircraft, connected to the turret through electrical cables carrying control signals. This approach offered multiple advantages that would prove crucial to the B-29's performance. Smaller turrets meant less drag, translating to higher speed and greater range. Reduced weight for each turret position allowed more ammunition to be carried. Pressurized crew compartments meant gunners worked in shirt-sleeve comfort at altitudes where unpressurized positions would require bulky heated suits. And most importantly, flexibility in connecting gunners to turrets through switchable electrical circuits meant each gunner could control multiple positions. The actual turrets designed for the B-29 demonstrated this philosophy. Each of the 4 remote turrets housed 2 Browning M250 caliber machine guns, the same weapons used throughout American aircraft but mounted in a compact spherical housing that rotated through 360 degrees in azimuth and traversed through extensive elevation and depression angles. The upper forward turret, positioned on top of the fuselage just behind the flight deck, could engage targets anywhere above and ahead of the aircraft. The upper aft turret, mounted further back along the fuselage spine, covered the upper hemisphere from directly above to the sides and rear. The lower forward turret, mounted in a retractable housing that lowered from the fuselage belly when deployed, provided protection for the underside of the bomber's forward section. The lower aft turret, in a similar belly position further back, covered the rear lower hemisphere. Each turret weighed approximately 450 pounds fully loaded, less than half the weight of a manned turret installation. The streamlined housings created minimal drag compared to the larger fairings required for traditional turrets. And the concentrated firepower of 850 caliber machine guns in 4 positions could be directed by as few as 2 gunners through the central fire control switching system. But the turrets themselves were merely mechanical actuators. The true innovation lay in the fire control computers that directed them. 5 General Electric analog computers, each the size of a large briefcase, were distributed throughout the aircraft. These were not digital computers in the modern sense. They were electromechanical devices using relays, servo motors, gear trains, and synchro resolvers to perform continuous calculations based on electrical inputs from the sighting stations. Each sighting station consisted of a periscope sight with a reticle that the gunner positioned on the target. As the gunner tracked the target through his sight, moving the reticle to follow the enemy fighter's motion, synchro transmitters converted these movements into electrical signals representing azimuth and elevation angles. These signals fed into the analog computer, which also received inputs representing the B-29's airspeed from the pitot-static system, altitude from pressure altimeters, temperature from thermocouples measuring outside air temperature, and angular velocity from rate gyroscopes detecting how rapidly the target was moving across the gunner's field of view. The computer processed all these inputs through a series of electrical and mechanical calculations happening continuously at speeds that would amaze engineers decades later. It computed the target's angular rate of motion, estimated the target's range based on the apparent size and rate of motion, calculated the lead angle needed to hit a target moving at that speed and range, compensated for gravity drop affecting bullets during their flight, adjusted for air density at altitude affecting bullet trajectory, corrected for the B-29's own motion through the air, and generated output signals that drove servo motors in the turrets, automatically positioning the guns to hit where the target would be when the bullets arrived. The gunner simply tracked the target through his sight and pressed the firing button. The computer did everything else. The calculations were not perfect. Analog computers lacked the precision of modern digital systems. Range estimation remained approximate, based on assumptions about target size and motion. But the system dramatically improved hit probability compared to manual gunnery where gunners estimated lead angles by eye and corrected based on observing their tracer rounds. The fire control system transformed novice gunners into effective defenders within hours of training. Even more significantly, the switching system allowed unprecedented flexibility in defensive coverage. At each sighting station, the gunner had switches that selected which turret or turrets his sight controlled. The bombardier in the nose could control the upper forward turret, the lower forward turret, or both simultaneously. The fire control officer stationed in the upper gunner position amidships could control both upper turrets. The two blister gunners, positioned at lateral windows along the fuselage, could each control both lower turrets. The tail gunner had a manned position with two 50 caliber guns plus a 20mm cannon in early models, and could override control of the aft turrets when needed. This flexibility created defensive capabilities that no previous bomber had achieved. If a fighter attacked from 12 o'clock high, directly ahead and above, the bombardier could bring both forward turrets to bear, concentrating 4 50 caliber machine guns on the target. If the attack came from 3 o'clock level, from the right side at altitude, the right blister gunner could control both lower turrets while the fire control officer controlled both upper turrets, creating crossfire from 4 positions. If multiple fighters attacked from different angles simultaneously, each gunner engaged his assigned sector, but could quickly switch turret control to concentrate fire as threats developed. The system also provided redundancy that improved survivability. If one gunner was wounded or killed, other gunners could take control of his turrets. If one sighting station was damaged, the turrets could be controlled from alternate positions. If electrical power to one computer failed, the system degraded but continued functioning through the remaining computers. The entire fire control system required approximately 2,500 pounds of equipment distributed throughout the aircraft. 5 analog computers, 5 sighting stations with periscope sights and control panels, for remote turrets with traverse and elevation servo motors, miles of electrical cabling connecting all components, ammunition storage for approximately 6,700 rounds of 50 caliber ammunition, and the manned tail position with its additional guns and fire control radar in later models. The weight penalty was substantial, but less than the weight of manned turret positions would have required, and the performance advantages justified every pound. Boeing's design team integrated the central fire control system into the B-29's overall layout with care bordering on obsession. The bomber was the most advanced aircraft in production anywhere in the world when development began in 1940, and every system needed to work together seamlessly. The pressurized crew compartments were critical to the remote turret concept. 3 pressurized sections divided by unpressurized bomb bays created environments where gunners could work effectively at altitudes exceeding 30,000 feet. The forward compartment housed the pilots, bombardier, navigator, and flight engineer. The center compartment, accessible through a pressurized crawlway running above the forward bomb bay, contained the fire control officer at the upper gunner station, the radio operator, and the two blister gunners at their lateral positions. The aft compartment, reached through another crawlway over the rear bomb bay, housed the tail gunner and the radar operator. This layout meant that gunners worked in shirt-sleeve comfort, wore minimal bulky equipment, and could focus on their tasks without the fatigue and distraction of extreme cold or wind blast. The improvement in gunner effectiveness compared to B-17 or B-24 crew members working in unpressurized positions was dramatic and immediately apparent during training missions. But the system's complexity also created vulnerabilities that would plague B-29 operations throughout the aircraft's service life. The Central Fire Control System represented cutting-edge technology pushed into production before all problems were solved. Early installations suffered from synchronization issues where the turrets did not track precisely with the sighting station inputs. Electrical connections failed under vibration. Servo motors burned out under continuous use. The analog computers, packed with relays and rotating components, proved sensitive to moisture, temperature extremes, and rough handling during aircraft maintenance. General Electric engineers worked continuously to improve reliability, issuing modification bulletins, replacing components, and training maintenance crews on the intricate system. But even with these efforts, the Central Fire Control System never achieved the reliability of simpler manned turret installations. The trade-off between capability and reliability would become a recurring theme in B-29 operations, forcing commanders to balance the advantages of advanced defensive firepower against the maintenance burden and system complexity. When the second B-29 prototype flew on December 30, 1942, it carried the first complete central fire control installation. The flight ended prematurely due to engine fire, but test pilot Edmund Allen reported that the defensive armament system showed promise during the brief time airborne. Subsequent test flights through 1943 refined the system through dozens of modifications addressing problems discovered during flight testing. Boeing and General Electric engineers learned through costly experience. By mid-1943, when B-29 production began in earnest at factories in Wichita, Renton, Marietta, and Omaha, the Central Fire Control System had evolved through multiple configurations. Production aircraft received systems incorporating lessons learned from prototype testing, but problems persisted. The first operational B-29 groups, forming in Kansas during late 1943 and early 1944, struggled with maintenance issues that kept the bombers grounded. Of nearly 100 aircraft delivered by the end of 1943, only 15 were considered airworthy. General Hap Arnold, commanding the Army Air Forces and personally directing the 20th Air Force that controlled all B-29 operations, intervened directly to resolve the crisis. He ordered factory personnel deployed to modification centers to work alongside Air Force technicians. He authorized extensive rebuilds of aircraft coming off production lines. He demanded accountability from Boeing and General Electric for system failures. The pressure achieved results. By spring 1944, when the 58th Bombardment Wing departed Kansas for India as part of Operation Matterhorn, the B-29s were marginally combat-ready. The Central Fire Control System still required extensive maintenance, still suffered failures that reduced defensive capability, but worked well enough for combat operations if properly maintained by trained specialists. The crews of the 58th Bombardment Wing would test this system under conditions its designers had never anticipated. Flying from bases in India, staging through forward fields in China, striking targets across thousands of miles of hostile territory, operating at altitudes where the bombers pushed the limits of their design, the B-29s would prove whether American engineering could deliver on its promises. And Japanese fighter pilots, scrambling to intercept these silver bombers that appeared suddenly in skies that had been safe from American attack for 3 years, would discover that everything they knew about bomber interception had become obsolete overnight. The first mission against Japan launched on June 15, 1944. 7 to 5 B-29s departed forward bases around Chengdu, China, bound for the Imperial Iron and Steel Works at Yawata on the southern island of Kyushu. Only 68 actually got airborne. 1 crashed on takeoff. The remaining aircraft climbed to altitude and turned east, crossing the China Sea toward targets they had studied in reconnaissance photographs and intelligence briefings. The mission plan called for a night attack at altitudes between 8,000 and 21,000 feet. Cloud cover over the target would prevent precision bombing, But the mission's primary purpose was not the physical destruction of Japanese steel production. It was announcement. For the first time since the Doolittle raid in April 1942, American bombers would strike the Japanese home islands. The psychological impact on Japanese civilians and military leaders would exceed any material damage the bombs might cause. At bases across Kyushu, Japanese fighter units received alerts as radar stations detected the approaching formation. The Fourth Air Regiment at Ozuki Airfield scrambled Kawasaki Ki-45 Toryu twin-engine heavy fighters, 24 aircraft lifting into the darkness to patrol over northern Kyushu where the bombers were expected to arrive. The 59th Air Regiment remained on the ground due to lack of coordination between units, mechanical problems with their fighters, and fear that the B-29s might spot and attack their base. The B-29s began arriving over Yawata at 38 minutes past midnight local time. Searchlights probed the darkness. Anti-aircraft guns opened fire, their shells bursting at estimated altitudes based on sound detection and visual sighting. The Japanese interceptors, flying through the darkness guided by searchlights and ground controllers, searched for targets among the scattered American formation. Warrant Officer Kimura found his target and made his attack. His experience that night, the shocking discovery of defensive fire from unexpected positions tracking his fighter with unnatural precision, would be repeated by Japanese pilots throughout the engagement. The Fourth Air Regiment claimed no confirmed kills during the interception. Multiple pilots reported engaging bombers, firing on targets illuminated by searchlights or silhouetted against clouds. But the B-29s seemed to absorb damage that would have destroyed conventional bombers and continued toward their targets. Only one B-29 was lost during the attack on Yawata itself, shot down by a determined attack that struck vital systems. The bomber, serial number 42-6230 called Limber Dragon, crashed with all 12 crew members killed, including Newsweek correspondent William Schenkel who was covering the historic mission. But the loss of one bomber from the attacking force provided little comfort to Japanese commanders who understood the strategic implications. American bombers had struck Japan from bases in China. If they could reach Kyushu, they could reach anywhere in the Japanese Empire once closer bases became available. And the defensive firepower displayed during the engagement suggested that intercepting these bombers would prove far more difficult than anticipated. Japanese after-action reports from the Yawata mission reveal confusion and frustration among pilots who engaged the B-29s that night. Multiple pilots reported that their attacks were detected far earlier than expected, that defensive fire came from turrets they had not visually identified, and that the fire seemed to track their fighters with unnatural precision. The Fourth Air Regiment's intelligence officers noted in their mission summary that American bomber defensive armament appeared to operate differently than the B-17s and B-24s encountered in other theaters, but they could not explain the mechanism. What the Japanese pilots had encountered was a defensive system designed specifically to counter the attack tactics they had perfected through years of combat experience. Every standard approach angle Japanese pilots used, head-on attacks from 12 o'clock high, diving attacks from above and behind, slashing passes from beam angles, climbing attacks from below, had been anticipated by American designers who studied Japanese fighter tactics through captured documents, prisoner interrogations, and combat reports from the Southwest Pacific and China-Burma-India theaters. The General Electric Fire Control System neutralized advantages that Japanese fighter pilots had exploited against earlier Allied bombers. Against B-17s and B-24s, Japanese pilots learned to make multiple quick passes from different angles, forcing bomber gunners to shift between targets and creating confusion in the defensive response. Against the B-29, this tactic failed because gunners could transfer turret control instantly through electrical switches, concentrating fire on the primary threat regardless of approach angle. Against conventional bombers, Japanese pilots exploited blind spots in defensive coverage where individual turrets could not traverse to engage attackers. Against the B-29, blind spots were minimal and covered by overlapping fields of fire from multiple turrets that different gunners could bring to bear through the switching system. Against traditional bombers with manual gunnery, Japanese pilots counted on gunners missing deflection shots at high closing speeds and long ranges. Against the B-29, the analog computers calculated lead angles automatically, allowing gunners with minimal training to achieve hit probabilities that previously required years of combat experience. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The missions from China continued through January 1945, striking targets in Manchuria, Formosa, and Japan itself. But Operation Matterhorn faced insurmountable logistical challenges that limited its effectiveness. Every gallon of fuel, every bomb, every spare part for the B-29s based in China had to be flown over the Himalayas from India, a route called the Hump that was one of the most dangerous air routes in the world. Weather conditions over the mountains were treacherous year-round. Turbulence could tear aircraft apart. Ice could form rapidly, bringing down heavily loaded transports. Winds exceeded 100 miles per hour at altitude. The logistics were staggering and ultimately unsustainable. Supporting a single B-29 mission from China required multiple transport flights over the Hump. Each superfortress consumed massive quantities of fuel for the long flights to targets. The bombers needed constant maintenance using parts shipped from the United States across multiple continents. Bomb loads had to be transported, along with ammunition, hydraulic fluid, engine oil, tires, and countless other supplies. The effort consumed transportation resources that could have supported ground forces fighting in China and Burma. General Albert Wiedemeyer, who commanded American forces in the China-Burma-India theater, argued repeatedly that the B-29s should be deployed elsewhere where they could operate more effectively. His objections were overruled by General Arnold, who believed the psychological impact of bombing Japan from Chinese bases justified the logistical cost. But the capture of the Mariana Islands in June and July 1944 created an alternative that rendered the China bases obsolete. Saipan, Tinian, and Guam offered everything China lacked. Deep water ports for supply ships, construction battalions that could build massive airfields quickly, proximity to Japan, approximately 1,500 miles, allowing B-29s to carry maximum bomb loads without exhausting their fuel on the journey, and supply lines that could not be cut by Japanese ground forces. The 21st Bomber Command began operations from the Marianas on November 24, 1944, with a raid against the Nakajima aircraft engine plant at Musashino near Tokyo. 111 B-29s participated in the mission, the largest superfortress formation assembled to date. Japanese defenders scrambled everything available. The 10th Air Division, responsible for defending the Kanto Plain around Tokyo, launched approximately 100 fighters from multiple airfields. Pilots flying Nakajima Ki-45 Toryu fighters, Kawasaki Ki-61 Hien fighters, Mitsubishi J-2M Raiden interceptors, and older types like the Ki-43 Hayabusa engaged the American formation throughout its approach and withdrawal. The engagement revealed how completely the B-29's defensive capabilities exceeded Japanese expectations. Flight leader Yoshio Yoshida of the 70th Air Regiment, one of Japan's most experienced pilots with multiple combat victories against Chinese and American aircraft, led his formation of Ki-61 Hien fighters in standard head-on attacks from 12 o'clock high. The approach that had worked so effectively against B-17s and B-24s in Burma and China produced devastating results for Yoshida's formation over Tokyo. As the Japanese fighters began their attack run, diving from altitude toward the lead B-29 formation, defensive fire erupted from multiple turrets on multiple bombers simultaneously. The upper forward turrets on the lead bombers, controlled by bombardiers in the nose positions, tracked the diving fighters and opened fire at ranges exceeding 800 yards. The computed lead allowed by the fire control system meant that bullets arrived at the intercept point just as Japanese fighters reached that position in their dive. Yoshida's wingman, Lieutenant Akira Kawakita, took hits in his engine from the concentrated defensive fire and broke off his attack, his fighter streaming white glycol coolant from punctured radiators. Yoshida pressed his attack despite the defensive barrage, closing to point-blank range of 200 yards before firing his twin 20mm cannons and pair of 12.7mm machine guns. His shells struck the lead B-29's nose section, shattering plexiglass and damaging the bombardier's compartment, but the bomber maintained formation and continued toward its target. Yoshida's after-action report noted the same confusion that earlier pilots had experienced. The defensive fire came from turrets he had difficulty seeing. The tracer streams tracked his fighter throughout the attack run without the lag he expected from manual gunnery. Multiple turrets on the same bomber engaged him simultaneously, concentrating fire in a way that suggested coordination beyond individual gunnery actions. Japanese intelligence officers analyzing combat reports from the November 24 mission and subsequent raids developed theories about the B-29's defensive system. Some speculated that the bombers carried additional crew members dedicated solely to directing defensive fire, a partially correct assumption given the role of the upper gunner as fire control officer. Others theorized that radar somehow guided the turrets to their targets, an incorrect but understandable conclusion given the apparently automatic precision of the defensive fire. None of the intelligence assessments correctly identified the computer-controlled remote turret system as the key innovation. Japanese engineers, working from combat observations and examining wreckage from shot-down B-29s, could not reconstruct how the system operated. The analog computers, when recovered from crash sites, appeared to be sealed electrical boxes with no obvious connection to gunnery functions. The turret servo mechanisms were too damaged by crashes or intentional destruction by surviving crew members to reveal their operation. By December 1944, Japanese home defense units faced an impossible tactical problem. The B-29s flew at altitudes where many Japanese fighters struggled to reach combat altitude before the bombers passed overhead. The extreme cold at 30,000 feet froze guns, thickened hydraulic fluid, and degraded engine performance. Pilots wearing multiple layers of clothing against the cold suffered from hypoxia at altitude despite oxygen systems that functioned poorly in extreme conditions. And when Japanese fighters did reach the bombers, the defensive firepower proved far more effective than anything previously encountered. Captain Fujitaro Ito of the Fifth Air Regiment emerged as one of the few Japanese pilots who developed tactics that worked against B-29 formations. Flying a Kawasaki Ki-45 Toryu twin-engine heavy fighter armed with 37mm and 20mm cannons, Ito specialized in close-range attacks from 12 o'clock level, approaching from directly ahead at the same altitude as the bombers. The tactic required extraordinary nerve. Ito would hold his course directly into the approaching formation, closing at combined speeds exceeding 500 miles per hour, waiting until the range decreased to 100 yards or less before firing his cannons and immediately braking down and away to avoid collision. The extremely short firing window, perhaps 2 seconds from trigger press to breakaway, demanded flawless timing and aircraft control. But the tactic worked because it minimized exposure to defensive fire. The B-29's forward turrets had limited depression angles and could not track targets approaching from directly ahead and level once they closed inside a certain range. The brief exposure time gave defensive gunners almost no opportunity to achieve accurate hits despite the fire control computers. And Ito's heavy cannons, particularly the 37mm weapon, could destroy a B-29 with a few well-placed hits to the cockpit or engines. Ito's success, 17 confirmed B-29 kills by war's end, demonstrated that determined pilots using optimal tactics could still destroy the superfortresses despite their advanced defenses. But Ito's achievements also highlighted how rare such success had become. Of thousands of Japanese pilots who engaged B-29 formations between November 1944 and August 1945, only a handful achieved comparable results. The tactics demanded skills and discipline that most pilots, particularly the inadequately trained replacements joining units in 1945, simply did not possess. Japanese home defense forces adopted increasingly desperate measures as the B-29 campaign intensified. In November 1944, the Imperial Japanese Army Air Force formed special attack units dedicated to ramming B-29s. Pilots flying Kawasaki Ki-45 fighters stripped of armor and some weapons to improve high-altitude performance would deliberately collide with bombers, destroying both aircraft but guaranteeing the bombers' destruction. The first confirmed ramming attack occurred on December 7, 1944, when Sergeant Shinobu Ikeda of the 25th Independent Unit rammed his Ki-45 into Captain Roger Parrish's B-29 called Galloping Goose over Mukden. Both aircraft crashed, killing all aboard. Ikeda received posthumous recognition as a war hero. More ramming attacks followed as Japanese commanders emphasized the tactic as the most reliable method of destroying B-29s. On December 3, 1944, Emperor Hirohito established the Bukosho, a decoration equivalent to the Medal of Honor, specifically to recognize pilots who successfully rammed enemy bombers and survived. The creation of this award signaled official imperial approval of ramming tactics as a legitimate air combat method. 3 surviving ramming pilots became the first recipients, their actions celebrated in propaganda that encouraged other pilots to follow their example. The ramming campaign achieved some successes. American records indicate that several B-29s were lost to deliberate ramming attacks, though the exact number remains uncertain because rammed bombers were often recorded as shot down by conventional fighter attack. Japanese claims of ramming kills significantly exceeded confirmed American losses, as was typical of aerial combat claims on all sides. But the tactic's effectiveness declined sharply after April 1945 when American P-51 Mustang fighters began escorting B-29 formations from Iwo Jima. The capture of Iwo Jima on March 26, 1945, after one of the bloodiest battles in Marine Corps history, provided the Americans with an airfield only 660 miles from Tokyo. P-51D Mustangs of the 7th Fighter Command began flying escort missions in April, and their presence fundamentally changed the tactical equation for Japanese fighter pilots attempting to intercept B-29 formations. Japanese fighters approaching to ram bombers now had to fight through American escort fighters first. The Mustangs, with performance superior to most Japanese fighters and flown by well-trained pilots, destroyed Japanese interceptors before they could reach the bombers. Ramming attacks required the Japanese pilot to focus completely on his approach to the target bomber, making him vulnerable to attack from escort fighters he could not evade while committed to his ramming run. The losses among Japanese ramming pilots increased dramatically once escorts appeared. The special attack units suffered casualty rates exceeding 90% by May 1945. Most pilots died without reaching their targets, shot down by escort fighters or killed by B-29 defensive fire before achieving collision. The survivors faced immediate attack by other escorts who pursued damaged Japanese fighters as they attempted to disengage after ramming attempts. Meanwhile, the B-29 campaign expanded to include low-altitude night incendiary raids against Japanese cities. On March 9, 1945, General Curtis LeMay, commanding 21st Bomber Command, ordered a radical change in tactics. 334 B-29s would attack Tokyo at night from altitudes between 5,000 and 8,000 feet, carrying maximum loads of incendiary bombs and with most defensive armament removed to increase bomb capacity. The decision to strip the bombers of defensive weapons seemed insane to many crew members who questioned the order. But LeMay's reasoning was sound. Japanese night fighter forces lacked the numbers, training, and equipment to effectively intercept low-altitude raids in darkness. Anti-aircraft fire, while intense, was poorly coordinated and inaccurate at night. The weight saved by removing guns and ammunition allowed each bomber to carry additional incendiaries, dramatically increasing the raid's destructive potential. The Tokyo raid on the night of March 9 to 10 proved LeMay's assumptions correct. Despite the reduced defensive armament, only 14 B-29s were lost from the attacking force, a loss rate of 4%. The destruction inflicted on Tokyo exceeded all previous raids combined. Approximately 16 square miles of the city burned. Japanese estimates of civilian deaths ranged from 80,000 to 100,000, though exact figures remained uncertain. More than 1 million people were left homeless. The success of the low-altitude incendiary tactics led to their adoption for most subsequent B-29 missions against Japanese cities. The remote-controlled turrets, so carefully designed and so effective against fighter attack, became largely unnecessary for the firebombing campaign. Many B-29s flew stripped of all defensive armament except the tail guns, carrying maximum bomb loads that devastated Japanese urban centers throughout the spring and summer of 1945. But the technological achievement represented by the Central Fire Control System remained significant regardless of whether the system saw combat use on every mission. American designers had solved a fundamental problem in bomber defense, creating an integrated weapons system that dramatically improved defensive capabilities while reducing crew exposure to hostile conditions. The system proved that remote-controlled weapons directed by analog computers could work reliably in combat, validating concepts that would shape military aviation development for decades. Japanese pilots who survived encounters with B-29s and lived to see the war's end almost universally praised the bomber's defensive capabilities. In post-war interviews, former pilots described the B-29's turrets as the most effective bomber defense they encountered, superior to anything mounted on B-17s, B-24s, or any Allied bomber type. The combination of coordinated fire control, automatic lead computation, and flexible turret allocation created defensive firepower that exceeded the sum of its individual components. The production statistics of the B-29 program revealed American industrial capacity at its peak. Boeing's plants in Wichita, Kansas, and Renton, Washington, Bell's plant in Marietta, Georgia, and Martin's plant in Omaha, Nebraska, produced 3,970 B-29s between 1943 and 1946. Peak production in March 1945 reached 357 aircraft delivered in a single month, more than 12 bombers per day across all production lines. Each B-29 cost approximately $640,000 in 1945 currency, approximately $9 million in 2025 terms. The total program cost, including research, development, testing, production, and support infrastructure, exceeded $3 billion, making it the most expensive military program of World War II, surpassing even the Manhattan Project's cost of $1.9 billion. This enormous investment produced a bomber that fundamentally altered strategic bombing doctrine and demonstrated capabilities that shaped post-war aviation development. The remote turret system, pressurized crew compartments, long range exceeding 3,000 miles, high-altitude capability above 30,000 feet, and heavy bomb load capacity of 20,000 pounds made the B-29 the most capable bomber of its era and a preview of strategic bombers that would dominate the early Cold War. The Central Fire Control System itself saw limited application beyond the B-29 and its derivative, the B-50 Superfortress. The advent of jet-powered bombers and air-to-air missiles rendered manned defensive armament obsolete for strategic bombers. The Boeing B-47 Stratojet, entering service in 1951, carried only a tail turret for defensive armament. The Boeing B-52 Stratofortress, the icon of American strategic bombing throughout the Cold War, relied primarily on electronic countermeasures and escort fighters for defense rather than gun turrets. But the legacy of the B-29's fire control innovation extended far beyond bomber defense. The analog computers developed by General Electric demonstrated that complex calculations could be performed reliably in real time using electromechanical systems. This technology informed development of fire control systems for naval vessels, anti-aircraft artillery, and eventually guided missiles. The concept of remote weapons control through electrical signals led directly to modern weapon systems where operators control weapons from great distances through electronic interfaces. The statistical record of the B-29 campaign against Japan demonstrated both the aircraft's capabilities and the limits of defensive firepower against determined opposition. American records indicate that approximately 520 B-29s were lost in combat operations against Japan, from all causes including fighter attack, anti-aircraft fire, accidents, mechanical failures, and weather. Of these losses, approximately 74 bombers were confirmed destroyed by Japanese fighters in air-to-air combat. The low loss rate to fighter attack, less than 1/4% per sortie in the campaign's final months, vindicated the B-29's defensive design. Japanese fighter opposition, while courageous and occasionally effective, could not inflict losses sufficient to halt or significantly impede the strategic bombing campaign. The combination of defensive firepower, altitude capability, and formation tactics made the B-29 the most survivable bomber deployed in any theater during World War II. Japanese pilots' experiences fighting B-29s revealed the psychological impact of facing weapons systems that exceeded their tactical doctrine's assumptions. Pilots accustomed to success against earlier Allied bombers found themselves unable to reliably intercept and destroy the superfortresses despite using the same tactics that had worked previously. The defensive fire came from unexpected positions, tracked fighters with uncanny accuracy, and concentrated from multiple turrets simultaneously in ways that suggested coordination beyond individual gunner capability. This technological gap, combined with fuel shortages that limited training for replacement pilots, inadequate high-altitude capability in many Japanese fighter types, and the increasing presence of American escort fighters after April 1945, rendered Japanese home defense increasingly ineffective during the war's final months. By July 1945, B-29 formations flew over Japan with virtual impunity, striking targets with minimal opposition. The two atomic bomb missions against Hiroshima and Nagasaki in August 1945 represented the culmination of the B-29 program. Though these special missions utilized modified silverplate B-29s with most defensive armament removed to reduce weight for the special weapons. The Boeing B-29 called Enola Gay that delivered the first atomic weapon on August 6, and Boxcar that delivered the second weapon on August 9, flew essentially unarmed except for tail guns, relying on escort fighters and surprise for protection. But these final missions succeeded because the B-29 program had demonstrated American ability to strike Japan at will from bases the Japanese could not reach or neutralize. The psychological impact of the atomic weapons combined with the realization that Japan could not defend against continued conventional and nuclear attacks contributed to Emperor Hirohito's decision to accept surrender terms announced in the Potsdam Declaration. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.